Welcome back, mathematicians. We are taking a little bit of a detour. We ended chapter 4 with 4.6, but we're actually going to go back to 4.8 a little later. I just kind of want to set up 4.8 a little bit better with the first two sections of chapter 5, which is all about integrals. I love integration. You're probably like, I have no idea what this means. We're going to figure it out in a little bit. So first we're going to talk about section 5.1, area and estimating with finite sums. So kind of the motivation behind this is that we don't really have a simple geometric formula to find the area below the curve of y equals 1 minus x squared, right? I don't know. I have like the area of like a rectangle, triangle, trapezoid, circle, sphere, all these, but I really don't know how to find this little blue area right here that I'm drawing. And note when we are finding these areas, the x-axis is kind of our stopping point, right? And this will give us a positive area. We'll go on more if once a curve goes below the x-axis, but currently we're always trying to find the area above the x-axis, all right? So we can estimate the area just like we could estimate the instantaneous rate of change before we knew about derivatives. So we didn't know about derivatives and tangents, but we knew how to estimate a slope. So we don't know about integrals and antiderivatives, but we know how to estimate area under the curve. So that's kind of why I want to set up before we go on to 4.8. All right. So the easiest area to calculate, in my opinion, are rectangles. Usually we call them length times width. In this case, we'll also go by base times height. So let's take the interval from 0 to 1 and let's split it into two intervals. If I just make a one big square out of 0 and 1, I'm not going to get a very accurate area. So it's kind of best to split it into two. So we split our 0 to 1 into two subintervals, 0 to 1/2 and 1/2 to 1. All right, so we call the base of a rectangle B, and it's going to be from 0 to 1/2 and 1/2 to 1. Well, what about the height? So I can either make my rectangle, I think this is the color, kind of look like, I can have 2 points in this first area. Let's call this A1 and we'll call this one A2. Well, I have this point right here or this point right here to choose from to be my height. We can choose our height for each interval, or subinterval, excuse me, but we have to stay consistent. So I can choose the upper sum or the lower sum. And what that means is I'm going to look at the endpoints of my subinterval. So at 0, f of 0, and at 1/2, f of 1/2. And I'm going to choose which one is larger. So I can choose and make this my rectangle. And similar for 1/2 to 1, my max between f of 1/2 and f of 1, that's 0. So I would choose this. And that would be my upper sum. So I can write that out. My notes are on the right page. There we go, okay. So right, so the area of 1 plus the area of the second one is going to be our base times our height. Well, our height is going to be the maximum of f of 0, f of 1/2. So it's going to be max of, not x, plus b times, right, our base times the max of f of 1/2 plus f of 1. Well, that equals b times f of 0 is higher than f of 1/2. So f of 0 plus b. And f of 1/2 is higher than, or sorry, greater than f of 1. That should be a comma. There we go. So in this case, the difference between 0 and 1/2 is 1/2. So that's our b. F of 0 is 1 plus 1/2, which is b again. And f of 1/2 is 1 minus 1/2 squared. So 1 minus 1/4 is 3/4. Right? And that equals 0.875. Right? So we take the upper sum, and it's going to be our base times our height plus base times our height of each rectangle. And our height is going to be chosen between the greater endpoint. So whichever endpoint is higher. All right? So lower sum works similarly, where I'm going to choose the lower of them. So for A1, that rectangle, f of 1/2 is the smaller one. So I can write that A1 plus A2 equals b times the minimum of f of 0, f of 1/2, plus b times the minimum, my second one, which is f of 1/2, f of 1. So choosing lower and upper sums is a really good way to kind of get a bound of what the area is, right? The upper sum is always going to be greater than the actual sum, and lower sum is always going to be smaller, just by definition. If I'm choosing the greater of the two numbers, I'm going to be overestimating it, as you can see right here in the green. So with the lower sum, b times f of 1/2 plus b f of 1, which is going to equal 1/2 times 3/4 plus 1/2 times 0, which equals 3/8, which is 0.375. So if we go up here and draw the red rectangles, and you can see right here, this one isn't even a rectangle. It's kind of like a line. So our green rectangles are upper sum. It's going to be an overestimate, right? It's counting all of this area right here that I don't necessarily want to count. Where the red is missing this area under the curve. And like in the second rectangle, we're not even counting any of the area. So it's a really big estimation. All right, so now let's take the interval 0 to 1 and split it into 4 subintervals. So I go from 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and 3/4 to 1. All right, let's do the upper and lower sum here. So we're gonna do b times, let's draw, I think I use this lime green. So my upper sum I have to draw these little lines. I forgot. This line. There we go. So I have these 4 green rectangles that I'm going to calculate the area of. Right, so each base is going to be 1/4 this time, right? From 0 to 1/4 is 1/4. 1/4 to 1/2 is 1/4 again, right? So if I'm going to do my upper sum, I can see that f of 1/2 is, sorry, f of 0 is the larger one out of the first rectangle, and f of 1/4 is the largest in the second. 1/2, 3/4, and those are our 3 points. Note you're choosing the max in point, not the max over the 0 to 1/4, 1/4 to 1/2, over the subintervals, just the end points. That would be really difficult to find. So f of 0 plus base times f of 1/4 all right, and those simplify to 1/4 times 1 plus 1/4 times 3/4. Oh no, 1/4 times 15/16 plus 1/4 3/4. There we go. Plus 1/4 7/16. And this simplifies to 25 over 32, which is equal to 0.78125. All right. So now we're doing the lower sum. So I'm going to choose the lower endpoint to make my height of my rectangle. So this way, f of 3/4, and f of 1 again. So now we have these red rectangles. Realizing now that the lime green is not the best, but I committed. So the lower sum, b times f of 1/4, because that's the lower out of f1 and f1/4, plus b times f of 1/2, plus b times f of 3/4, plus b times f of 1. All right, and then I can plug in, my base is 1/4, ooh, no spoilers, 15/16 plus 1/4, 3/4 plus 1/4, 7/16 plus 1/4 times 0. So that's going to simplify to 17/36, which is 0.53125. All right. So notice that with more intervals, the upper sum decreases, right? It was at 0.875 and now it decreased to 0.78125. And the lower sum increases. So it was at 0.375 and it jumped up to 0.53125. All by splitting those intervals in half again, those subintervals. And then I kind of also drew a chart. All right, so my upper sum with 2 intervals, 0.875, it decreased to 0.78125. And lower sum we talked about increased. So by definition, the upper sum is always going to be greater than the lower sum. So what does that mean? What happened when I add more and more subintervals. The upper sum is going to have to decrease down to something, and the lower sum is going to have to increase to something. So I spent way too much time, and I drew the graph with 16 subintervals. So the top one here is calculated with upper sum. And you can see the overestimation on these little almost triangle things. And we have our lower sum in red. And I colored them in. This took way too much time. And we still have this underestimation. But I have a lot less of an underestimation than I did right here. This area is so much bigger than the area I missed here. Look how much smaller that, when I calculated that to be 0. That's significantly smaller than this entire area. Okay? So, here we use 16 subintervals. We denote n as the number of subintervals. In this case, I use 16, so n is 16. The width oh my gosh. The width of each interval is equal. It's the same. I'm not going to change it. We'll talk about next section briefly about why some people might change them. I'm not a fan of that. Earlier we called the width b for base, but we like to call our intervals a to b, so we call that now delta x, right? Because remember how we made b be the on the x-axis, so it's going to be the change in x. It's our independent variable. Sometimes it might be delta t, delta r for radius, and whatever your independent variable is. So on the interval AB, we can find delta x with this nifty formula. So b minus a divided by n, the number of subintervals, excuse me. So if we call c of n some x value in the nth subinterval, so we've seen how it's going to be the larger of the endpoints. It's going to be the smaller endpoint, right, in the upper and lower sum. We can estimate the area under f of x over the interval AB by using the finite sum, where I add f of c1, so that number in the first subinterval, times my delta x, times my base, plus f of c2 in the second subinterval, times delta x again, so on until adding those all up until I get to f of cn, my nth subinterval, times delta x. So we kind of saw that up here. Remember, I kept multiplying by 1/4 and 1/4 and 1/4 and 1/4. That's my delta x. Right? So 1/4, 1/4, 1/4, and so on. We can also pull out that common term, right? Delta x times f of c1 plus f of c2 plus all the way over to f of cn. So when we're adding all these up, it might be better to pull out delta x and then add all those function values together and then multiply by delta x. All right, so there's many different types of sums to estimate the area under the curve, right? I just said cn needed to be some value in that subinterval. Usually we like to do with endpoints, just because it's really easy to find those values since we're already given the endpoints of the intervals, because we needed to find them to get delta x. So if we let AB be divided into n subintervals with endpoints x0, x1, all the way up to xn, so like x0 to x1, that's your first subinterval, and so on, x1 to x2 is your second, and so on. So one sum is called the left endpoint sum. So we're going to use the left endpoint of each subinterval to find the height of the rectangle. So I'm not going to look at f of x0 and f of x1 and see who's bigger. I'm just going to choose f of x0 for my first subinterval. I'm not going to look at f of x1 and f of x2 to see who's the largest. I'm just going to choose f of x1 for my second subinterval. So we can write that area, whoopsies, will equal, oops, that's an A, delta x times f of x naught, or x0, plus delta x, f of x1, all the way to my last interval. So my last interval is going to be x n minus 1 to x to n. So this is going to be f of x n minus 1, because I need to choose the left endpoint. So that means that x sub n is going to be on the right, so I'm not going to choose him at all. And then I can also rewrite this, pulling out my delta x. So we're going to add up. Oops. Beautiful. All right, so right endpoint is pretty much the same. So we're going to use the right endpoint of each subinterval to find the height of the rectangles. So that means our area is going to equal delta x times f of x1 for my first rectangle, plus delta x f of x2 plus delta x f of x n. So I'm not choosing the first endpoint x0 because it's the left of the first one. So left endpoint, I'm leaving out x sub n, my last endpoint. Right endpoint, I'm leaving out my first endpoint, x sub 0. And similar to what I did above, I can pull out my delta x. The advantage of doing left and right endpoints is it's not going to give me like an upper bound and a lower bound. It's going to kind of be a little bit more consistent in telling me a better estimate, because I'm not choosing favorites. Oh, this one's going to be higher. Oh, this one's going to be less. So now we have the midpoint. So we're going to use the midway or halfway point of each subinterval to find the height of the rectangle. So what halfway point means is the halfway point of the x's. So if I go, what's a better picture? Right here, from 0 to 1/4, I'm going to choose 1/8 to be my rectangle. So I would like to make my rectangle right here. I'm not choosing halfway between f of 0 and f of 1/4. I'm choosing halfway between 0 and 1/4. It's fine, midpoint, there it is. So that area, this one is, since you're kind of averaging something, it's a little bit better of a thing, estimate, sometimes. So delta x f, so we're going to take the average between x of 0 and x of 1 over 2, plus delta x f of the average between x1 and x2, plus dot dot dot, all the way until we get to delta x times f of xn minus 1 plus xn over 2. All right, and again, I can pull out that delta x. So those are three other ones other than upper and lower sum. We have left endpoint, right endpoint, and midpoint. So there's some other sums that we won't discuss because of timing, and it's not in your textbooks, which I think is weird. But they're really cool. Trapezoid rule or method, it's often called, is really, really cool. It's my favorite. If you remember, the area of a trapezoid is the average of the bases, which in this case, so like if this is your base and then something like this, that's your trapezoid. So the height is actually right here, and then you have like H1, H2. So basically you average your function values and multiply them by your base, and that's how you get the area of each little guy, which we're not going to do. Simpson's rule is something similar, but instead of sometimes you have 2 and sometimes you have 4, and then there's some 3's involved. This one's crazy. I would look it up though because it's really cool. Okay, cool. So what's the point of finding the area under the curve? It's because I can now go from, in derivatives, we went from position to velocity to acceleration. Well, now I can go the opposite way. I can find the total distance traveled of an object by using just velocity alone. So remember, velocity is going to be v of t. That looks like not v. There we go. And position we called s of t. We talked about this, I believe, in section at least 3.4, if not more earlier in chapter 3. So there's a difference between total distance traveled and displacement. So displacement is the difference between start and finish. So if I'm going from A to B, S of B minus S of A, that's going to be my total displacement. If I start at my house, I go to Target, I come back, my total displacement, I stopped where I started, is 0. But my total distance traveled is like 10 miles. Because it's 5 miles there and 5 miles back. But what if I took a different route? Stuff like that. So total distance traveled is given by this fun little equation that should look similar to what we just did. So I have delta t times the absolute value of velocity at t1 plus the velocity at t2 plus all the way up to the absolute value of the velocity at tn. The reason we're doing absolute value is because velocity can be negative, right? If we're traveling back down towards something, like back down towards the ground, that's a negative velocity. I don't want that to cancel out with distance that I've already traveled. So I need to take the absolute value. So I'm technically doing the speed of it, right? Remember, speed is the absolute value of velocity. All right, so we did the rock problem back in section 3.4, right? Our rock was blown up by a dynamite, and we were given that its velocity we found to be 160 minus 32 t feet per second, right? We saw that at t equals 0, rock was still on the ground, and it landed, and we found that it landed again on the ground at t equals 10, and that it reached its maximum height of 400 feet at t equals 5. Now, it wouldn't be really interesting if I was like, oh, the total displacement over 0, 10. Well, if I was on the ground and I went up and went back out and now I'm on the ground again, my total displacement is 0. My total distance traveled is 800. I went up 400 feet and I came back down 400 feet. So let's look at a more interesting subinterval, which is 0 to 8. I went up to my max and I'm almost all the way down. So let's use 16 subintervals, and we're gonna do left and right point. So if we use 16 subintervals, delta t is gonna be 8 minus 0 divided by 16, which is 1/2. So I'm gonna write that, use left and right. Okay, so when you're asked to do more than one estimate, So if you're asked to do upper and lower or left and right, it's best to make a chart with all your functions, so all of your f of x ins, so summing is a lot easier. So here's my little chart. I haven't gotten there yet to plugging in all those numbers. This is also really good for upper and lower because you can kind of look at, okay, these are my endpoints of subinterval 1. Which one's bigger? That one. Subinterval 2, between 0.5 and 1, and so on. So it's really helpful for that. And also when you're doing more than one, it's really easy to kind of go back and like, oh, here's all my information, this one little area. All right, so if I plug in all my points into my velocity equation, I will get, this is 160, 144. I'm not putting units on these just because we know that they're all feet per second. So I can put feet per second right there. So 112, 96, 80, 64, 48, 32, 16. At 5 is 0, right? That's our maximum. And then I'm going to come back down. And now I'm falling, so it's negative 16, negative 32, negative 48, negative 64, negative 80, and negative 96. Okay, perfect. So for my right endpoint, I'm going to, my delta t I know is 1/2. So I'm going to do 1/2 times, and my right endpoint. Sometimes writing a chart up and down like this, it's kind of confusing to see who's left and right. I originally had it going horizontal, but it took up too much space. And so my right endpoints, if you scroll back up and look at it, I'm going to, where are you? Use every point except for the first one, f of x is 0. So I'm going to add all of these numbers up except for 160. So I'm going to do like 144 plus 128 plus plus the absolute value of like negative 80 plus the absolute value of negative 96, right? So all of these are going to have an absolute value around them. And that will give me a whopping total of 528 feet traveled. All right, so with my left endpoint, I'm going to use every value except for my last one, negative 96. So I'll do 1/2, 160. So now I'm including that first one plus 144, everything in between, and then absolute value of negative 64 plus absolute value of negative 80. And that's going to equal 560 feet, which is pretty cool. So the actual distance is 544 feet. And we'll learn how to do that tomorrow, the next 2 chapters. So both of them are 16 feet away from the actual answer, right? So left and right endpoints will give you a better estimate on either side. So left endpoint and right endpoint, the difference between what's actual answer will usually be the same. Where upper and lower sum, we saw how the upper sum was kind of a better estimate most of the time. Well, not better. It didn't always change too much compared to the lower sum. All right. So I think that's all. Yep. That's all for 5.1. And now we're going to move on to 5.2, and we're going to talk about more about how those limits, right, as the upper and left sum, as I add more and more of those little subintervals, and how I can get to a better estimate. All right, so I'll see you guys there.